Hello everyone, this is Professor Ng Chi Kun from Unimas. In this video, I'm going to give you a tutorial solution on approximate analysis of statically indeterminate frame with lateral loads using Porter method. So for this question, you're asked to use the Porter method of analysis and then draw the moment diagram for Girder F, E, D. So in this case, we are going to use the assumptions that we made in Porter methods. So first of all, we have to put hinges at the middle of each segment. So these are considered zero moment points or inflection points, okay, or hinges. Okay, so in this case we need extra markings. So we say that this one is A, B, C, D, E, F. So it goes G, H, I, J, and K. So for the first step, we are going to detach this frame at hinges G, I, and K. So with that, you look like this. Okay, we detach the hinges at G, I, and K, and we have external forces. We have an external force of 15 kilonewton acting at joint F here, and we know that the shear force at the exterior column is V, the shear force at the interior column is 2V, and then we have the exterior column shear force V here. Okay, and then we assume that this column is in tension, so we assume that there is an axial force of Gy going away from the hinge, and then we assume that this column is in compression, so Iy is upward, and then this column is in compression, so Ky is upward. So using equilibrium equation of total Fx equals to 0, we have 15 minus V minus 2V minus V equals to 0. So we have 15 minus 4V equals to 0. So V equals to 15 over 4. So V is 3.75 kilonewton. So here we have V 3.75 kilonewton, 2V 7.5 kilonewton, and V 3.75 kilonewton. So that is the only solution that we can get from this free body diagram, because we have three more unknowns, which are Gy, Iy, and Ky, but we only have another two equilibrium equations, so we cannot solve for three unknowns with just using two equations. So next, we move on to detach another hinge at H here. Okay, so H is here, so we're going to detach H and then isolate GFH as a free body diagram. So GFH will look like this. So just now we already know that V is 3.75 kilonewton, and we don't know Gy, and we have detached H away. So H is a hinge, so a hinge will have a vertical unknown force and a horizontal unknown force, Hx. So in this case, we assume hx is from right to left and then hy is upward. So by using total forces in horizontal direction equals to 0, so we have 15 minus 3.75 minus hx equals to 0. So we solve for hx, we get hx equals to 11.25 kilonewton. And then second step is to sum moment at joint H. So when we want to sum moment at joint H, we sum moment at joint H. So in this case, hx, hy, and also this 50 kilonewton force goes to point H. So these three forces will not produce any moment about joint H. And then normally we sum moment, we take anti-clockwise moment as positive. So we have 3.75 kilonewton times 3 meter, which is clockwise, so negative 3.75 times 3 minus or plus, in this case, gy has a moment arm of 4 meter to h, so gy is producing an anti-clockwise moment. So we have gy times 4, which is positive, sorry. So gy times 4 minus 3.75 times 3 equals to 0. So solving for gy, we have gy equals to 2.8125 kilonewton, positive. So positive meaning that this assumed direction is correct, so it's downward. So next we move on to another free body diagram, which is HEJI. So for HEJI, we are going to get a free body diagram like this. So this joint is H, this joint is E. So E, we're not detaching it away from the frame, so this one remains as a joint without any external forces. Okay, and then for joint J, we detach it away from the hinge, so we have a horizontal force and a vertical force which are unknown, so we name it as Jx and Jy. And then Iy, we also don't know it in the first place. And then at joint J here, we have 2V, so 2V is 7.5 kilonewton. And then these two forces, this is a common joint with this joint H here. Okay, so this joint H here is a common joint with this joint. So all the forces must be complementary. So here we have Hx going from right to left. So the H here must be going from left to right. And then we have Hy going upward. So here we must Hy going downward. And these magnitudes are already known from the previous analysis. So the only three unknowns are Iy, Jy, and Jx. So now we sum total forces in the horizontal direction. So we have 11.25 minus 3. We don't know this force yet, so minus Jx, and then minus 7.5 equals to 0. So Jx from the solution is 3.75 kilonewton, positive. Positive meaning that the assumed direction is correct. And then next, we want to sum moment about joint J. We sum moment about joint J because Jy is an unknown, so that we want to eliminate Jy. So with some moment at joy j, so that joy jy is going through this point, so it doesn't create any moment. Okay, so left only this 7.5 kilonewton force, which will create moment at this point. This Iy also will create moment at this point. And then this 2.8125 kilonewton force will also create moment at this point. So the 11.25 kilonewton force here will pass through joint J, so no moment created by this force here. So Jx also passes through joint J, right? So we only need to look at this force, and this force, right? So Iy is an unknown. So now with some moment at joint J, and then take anti-clockwise moment as positive. Okay, so this force here with moment arm of 8 meters will have an anti-clockwise moment, okay, with respect to joint J. So the moment is 2.8125 times 8. And then Iy will create a clockwise moment about joint J. So minus Iy times 4 meter. And then this 7.5 kilonewton force will create clockwise moment about joint J as well. So minus 7.5 kilonewton times 3 meters. Solving for Iy from this equilibrium equation, we get Iy equals to 0. Then we move on to use the total forces in the vertical direction. Then we get minus 2.8125 kilonewton plus Iy, which is 0, plus Jy equals to 0. So solving for that, Jy is 2.8125 kilonewton outward force. So now all the unknowns has been solved. Next, we will move on to the other part of the frame. So the other part of the frame is JDK. Okay. So JDK, we are going to get a free body diagram like this. This is joint J, this is joint D, and this is joint K. Right? At joint K, we already know that there's a shear force B of 3.75 kilonewton. And then the forces at joint J here. So this joint J here and the joint J here is a common joint. So the forces must be complementary. So over here we have horizontal force going from right to left of 3.75 kilonewton. So in the other free body diagram of the same joint, the force must be going from left to right, opposite of the previous force. And this Jy is going upward, so this Jy must be going downward in the other free body diagram of the same joint. One is action, one is reaction. So the only unknown in this free body diagram here is Ky. So by just summing forces in the vertical direction, we have Ky minus 2.8125 equals to 0. So Ky equals to 2.8125 kilonewton. So we have already solved for Ky in this manner. So now we have already solved for all the unknown forces of Gy, Iy, and Ky with this solution. So now the question is asking you to draw a free draw a bending moment diagram for this girder here. Okay, so now we want to determine what is the moment of this girder at each of the joints. Okay, so in order to know what is the moment here, we can make use of this free body diagram, and then we have already solved for hx and hy, and then we just cut across a section here and isolate this as a free body diagram. Okay, so we just cut across a section here and then isolate this as a free body diagram. So this point here is point F. Okay, so we isolate segment FH as a free body diagram. So it will look like this. This is joint H, this is joint F. So when you cut across joint F here, because it's a fixed joint, so fixed joint we have 3 reactions. So in this case, we assume that Fy is going upward, and then Fx is in the horizontal direction from left to right, and then this MF here, we are taking positive direction of bending moment as the direction of MF. So if we have an element bending this way with moment like this and moment like this, we take this as a positive moment. So positive moment meaning that we have compression on top and tension at the bottom. So we define this type of moments causing compression on top of the element and tension at the bottom of the element as positive moment. So why MF is clockwise? Because the moment that we take as positive bending moment is clockwise on the left hand side of the element. So this is on the left hand side of this element FH. So we take this as the moment direction for MF. Okay, so meaning that this MF, if the direction is this way, then is a positive bending moment. If it's the opposite, then it will be a negative bending moment. So let us solve for MF. Okay, so to solve for MF, in order to eliminate Fy and Fx in the total moment equation, we are going to sum moment at point F, so that we can eliminate Fx and Fy in the equilibrium equation, because these two forces passes through joint F. Take note that Fy and Fx both passes through joint F. Okay, so this Hx also passes through joint F. These are the known forces that we have solved from the previous solution. Okay, so now we can sum moment at joint F. So by summing moment of joint F, so we take anti-clockwise moment as positive in this summing moment. Summation of moment MF equals to 0. So now we have MF, which is clockwise. Okay, so clockwise moment, we put it as negative MF. And then the next force causing moment is this HY. Okay, so HY is giving you an anti-clockwise moment about joint F. So anti-clockwise moment, we get the positive moment, and then the magnitude is 2.8125 times the moment arm of 4 meters. Okay, so there is no other force, so we equate that to 0. So solving for MF, okay, we have MF equals to 11.25 kilonewton meter. Okay, so in this solution we get MF equals to positive, so meaning that this assumed direction is correct. Okay, so meaning that MF will be a positive bending moment according to our sign convention here. Okay, where the moment in the clockwise direction at the left hand side of the element, this moment is a clockwise moment on the left hand side of the element, and it's clockwise, so meaning that this MF is a positive moment. Okay, so in the bending moment diagram, MF here is positive bending moment 11.25, so we already got a point here which is at joint F. Okay, so next we'll move on to this particular free body diagram here. So this is joint H. Okay, so this is joint H, and this is joint E. Okay, so we take segment HE as a free body diagram in this case. So how can we take HE as a free body diagram? Is just by cutting a section here, and then isolate this part of the free body diagram and isolate HE as a free body diagram. Okay, so once we cut across here and isolate HE as a free body diagram, we have something like this. Okay, this is joint H. So joint H, we already know the internal forces at this joint H is going in this direction as shown. And then we cut across joint E here, because joint E is a fixed joint, so we have 3 reactions. So we have EY, we have EX, and we also have ME. Okay, so all these are unknown forces, EY, EX, and ME. They are all unknown forces and moment. So as I mentioned, the direction of ME is also taken as the positive direction for the bending moment. because as I have explained just now, for sign convention of bending moment, we are taking the sign convention of bending moment this way, causing the bend of element in this manner, where compression on top and there's tension at the bottom. So bending moment that has this kind of attributes, we take it as positive bending moment. So this ME is on the right hand side of this element. So the right hand side of the right hand side moment for a positive bending element is anti-clockwise. So we put anti-clockwise moment for ME by taking the positive bending moment. So if we get ME as positive in the solution, then we know that the bending moment here is positive. If we get the opposite direction, then ME is a negative bending moment. So let us solve for ME. So to solve for ME, we may sum moment at joint E so that we can eliminate the two unknowns of EY and EX, so we don't have to know these two forces. Okay, so we just take a point where we sum the moment and it can eliminate the two unknown forces of EY and EX. So meaning that these two forces of EX and EY, they both passes through joint E, so they don't create any moment. So this 11.25 kN force also passes through joint E, so it doesn't create any moment about joint E as well. So now we want to sum moment about joint E, so we sum moment about joint E, and this has to be equals to 0. And then we need to have a sign convention for summing moment, so we take anti-clockwise moment as positive as usual for summing moment. Okay, so when we sum moment here, ME is anti-clockwise, so we have minus. ME is anti-clockwise, so we have positive ME. Okay, so positive, we don't have to put a positive in front of it, just ME. And then we have the 2.8125 kilonewton force that is producing an anti-clockwise moment about joint E as well. Okay, so anti-clockwise moment, we have positive 2.8125 kilonewton times its moment arm, which is 4 meters. Okay, so there is no other moment, so we equate this to 0. So solving for that, we get ME equals to minus 11.25 kilonewton meter. So the negative sign here means that it's opposite of this direction. Okay, so ME should be a clockwise moment. Okay, so if ME is a clockwise moment, then it's opposite of the positive sign convention of the positive bending moment. So the bending moment here is negative. Okay, So when we plot the bending moment diagram, ME is negative, right? 11.25 kilonewton. So ME has two values. Take note that ME has two values of bending moment. Okay, so ME, we have one bending moment on the left hand side of the joint. We have another bending moment of ME on the right hand side of the joint. When we cut across a section, so now when we cut across a section here and isolate this part of the frame as a free body diagram, so we're going to get another ME, but this ME is on the right hand side of joint E. Just now we have already calculated ME for the left hand side of the joint. Now we want to look at the ME at the right hand side of the joint by using segment EJ, right? So segment EJ will look like this. Okay, so this is joint J. Just now we already cut across a section at E. So E is a fixed joint, so there are three reactions. So we have EY, EX, and ME. So this ME is also assumed in the positive bending moment direction. Okay, so this ME is on the left hand side of the element. So on the left hand side of the element we have a moment which is clockwise for the positive bending moment sign convention. So we assume ME in the positive direction for the bending moment. So in this case, to solve for ME and by summing moment at joint E, we can eliminate EY and EX from the moment equation, or we can eliminate EX and EY from the equilibrium equation by summing moment at joint E. So when we sum moment at joint E, what are we going to get? Okay, so we know that this force of 3.75 kilonewton passes through joint E as well. So when we sum moment about joint E by taking anti-clockwise moment as positive, so we have ME which is clockwise. So we have minus ME, and then since this force passes through joint E, so no moment by this force, and then we have another force which has 4 meter moment arm to joint E, which is JY. So this force magnitude is 2.8125, and then it produces an anti-clockwise moment about joint E. So anti-clockwise moment is positive. So this is 2.8125 times 4 meters. So there is no other moment, so we equate this to 0. So solving for ME, we have ME equals to a positive value of 11.25 kilonewton meter. So positive value meaning that the assumed direction of ME is correct. So this ME is the same direction as the positive bending moment. So the bending moment on the right hand side of E is positive. So when we plot the bending moment diagram, the moment on the right hand side of E is 11.25, right? So just now we have bending moment at joint E on the left hand side of the joint is 11.25 negative, and then the moment on the right hand side of the joint E is positive 11.25. Okay, so there is no vertical load in between these two joints here, so there is no effect from external load, so we can just join a straight line from joint F here to joint E here, and then this bending moment will jump up to positive 11.25 again. Okay, so this is the bending moment on the left hand side of joint E. This is the bending moment on the right hand side of joint E. So now we have left only the last bending moment at this joint here for the girder. So that joint is joint D. So now we take segment JD as our free body diagram. So segment JD can be cut from this free body diagram. Okay, so if we cut across the section here and then isolate this part of the girder is as a free body diagram, so we are going to get something like this. Okay, so this is after we have cut across joint D. Okay, and the forces at the hinges are already known, okay, from the previous solution. So in this joint D here, we have three unknowns because it's a fixed joint. So when you cut across, there must be a vertical reaction. This should be D, not E. Sorry. Let me do the corrections here. So this is dy, and this is dx, and this is md. Okay. So similarly, we use positive bending moment convention to assign the direction, the assumed direction of MD. Okay, so this MD is on the right hand side of the element. So we look at the bending moment direction on the right hand side of the sign convention. So this is anti-clockwise, so we put MD as anti-clockwise. Okay, so if MD is in the assumed direction as what is indicated here, then MD will be a positive bending moment. If we get opposite direction, then the bending moment of MD will be negative. So let us sum moment at the joint D now. Okay, so we just sum moment at joint D. So when we sum moment at joint D, and then taking anti-clockwise moment as positive, so we sum MD, and then this should be equals to 0. So we have MD, which we assume to be anti-clockwise. So we have MD anti-clockwise, so it's positive, right? And then we have another force that has a moment arm to point D, which is this 2.8125 kilonewton force, and this force will produce an anti-clockwise moment about point D as well. So anti-clockwise moment is positive moment following the sign convention that we have set up just now. So this is 2.8125 kilonewton times moment arm of 4 meters. So there is no other moment, so we could get this to 0. So solving for MD, we have minus 11.25 kilonewton meter. So on the minus sign here indicates that MD should be a clockwise moment. Okay, it's not anti-clockwise, but it's the opposite. Okay, it's a clockwise moment. So clockwise moment is opposite to the positive sign convention of bending moment. Okay, so clockwise moment is opposite of this on the right hand side of the element. So meaning that the bending moment of MD is negative. Okay, so when we plot the bending moment diagram, MD is negative. Okay, so just now we got ME equals to positive 11.25, and then now we have got MD equals to negative 11.25. So these are bending moments, okay, and there is no external forces in between E and D. Okay, so we just join this bending moment with straight line. Okay, so finally this is the bending moment for girder FED. Right, so that's all for the tutorial solution for this question. Thank you very much for watching.